Okay, now we're going to see photoelectric effect. Okay, what is photoelectric effect? It is the phenomena of emission of electron from the surface of metals when radiation of suitable frequency fall on them. Okay, the emitted electrons are called photoelectrons, and the current so produced is called photoelectric current. Now, examples: the alkali metals like sodium, potassium, etc. show photoelectric effect with visible light, whereas the metal like zinc, cadmium, etc. are sensitive only to ultraviolet light. Now, this is the diagram of photoelectric effect. When light is okay, when light is on the metal surface, then the electrons are emitting. Okay, these these are photons and these are electrons. This phenomenon is known as photoelectric effect. Now, next is the Hertz observation. Okay, Hertz observations on photoelectric effect. Okay, the phenomenon of photoelectric effect was discovered by Heinrich Hertz in 1887. Hertz, while studying experimentally the production of electromagnetic waves by means of discharge, found that the high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Now, Halwak's and Leonard's observations. Okay, Leonard observed that if a potential difference is applied across the two metal plates, okay, applied across the two metal plates enclosed with an evacuated tube, no current flows in the circuit. When one plate emitter enclosed in the evacuated tube kept at the negative potential is exposed with ultraviolet radiation, current begins to flow. Okay, these observations indicate that when a UV radiation falls on an emitter plate, electrons are ejected from it. Now, in 1888, Hawkes connected a negatively charged plate to an electroscope and observed that zinc plate lost its charge when it was illuminated by UV radiations. He also observed that uncharged zinc plate became positively charged when it was exposed by UV radiations. The positive charge on the zinc plate was further enhanced when it was more illuminated by UV radiation. From this observation, Hallwachs and Leonard also concluded that there was no emission of electrodes from the emitter plate if the frequency of the incident light was smaller than a certain minimum value, and that value is called the threshold frequency. Now, the experimental study of photoelectric effect. This is a diagram, okay, of the experimental study of the photoelectric effect. This is the evacuated tube, and these are two electrodes. Now, when monochromatic light source is projected in one of the electrodes, then electrons from this photoelectric plate ejected, and it goes to the electrode of A. Then the circuit is complete and the electrons moves in this direction, though thus the current flows in this direction. The circuit complete and current flows. This is the whole scenario. Now, next is the apparatus consists of an evacuated glass of quartz tube which encloses a photosensitive plate P, which is the emitter, and a metal plate A collector collector, a transparent window W is sealed on the glass tube, which can be converted with a filter for a light or particular radiation. Now, when a monochromatic radiation of suitable frequency fall on the photosensitive plate of the photoelectrons emitted from B, which get accelerated towards plate A, which is a positive potential. This results in the production of photoelectric current. This experimental arrangement can be used to study the variation of photoelectric current with number 1 A. Intensity of light radiation, B. The potential difference between the metal plates, the frequency of incident radiation. Now, effect of intensity of the photoelectric current in the incident radiation. Okay, effect of intensity of the incident radiation. Now, in this graph, you can see this is the intensity and this is current. Okay, as the intensity increasing, the current is also increasing and the graph is linear. So what we can see here is intensity is directly proportional to current. Okay, this is the conclusion here, that intensity is directly proportional to current. Now, next, using a radiation of fixed frequency and keeping the plate A if at a fixed potential vary the intensity of incident radiation, it is found that the photoelectric current varies linearly with the intensity of light radiation. Now, effect of potential difference between the metal plates. Okay, we have seen the metal plates like this B and this is A. We have emitted the light from here and electrons are emitted from here. So what is the effect of potential difference between the metal plates? Okay, this is the graph. Okay, you can see more clearly. This I'm going to explain. Okay, this is the current and this is the potential difference. Okay, now let's see. If illuminated the metal plate B with radiation of fixed frequency and intensity vary the positive potential of plate A and note the photoelectric current, it is found that the photoelectric current increases gradually with the increase in the positive potential plate. Okay, here you can see. Now, on applying the negative potential to metal plate A with respect to metal plate B, the photoelectric current decreases. On increasing the negative potential of metal plate A, the photoelectric current decreases rapidly and becomes zero. The minimum negative potential given to the metal plate for the which the photoelectric current becomes zero is called the stopping potential. Repeat the experiment with the radiation of the same frequency but higher intensity. It is found that the saturation current becomes more with increase in intensity. Stopping potential remains same. Effect of frequency. Take the radiation of different frequencies per the same intensity. The variation between the photoelectric current and the potential of metal plate is given in the figure. Okay, this is the figure. The value of stopping potential is different but the radiation of different frequency. The value of stopping potential is more negative for the radiation of higher frequency. The value of saturation current is independent of the frequency. If we plot a graph between the stopping potential and the frequency of the incident radiation, we get the following graph. For the given photosensitive material, the stopping potential varies linearly with the frequency of the incident radiation. For a given photosensitive material, there is a certain minimum frequency called threshold for which stopping potential is zero. The threshold